Hello to everybody out there. Welcome to hour 3 of our journey through the machine learning world, cruising the machine learning world with HPCC Systems. Once again, my name is Bob Foreman. Welcome to hour 3 again. And with me is my esteemed colleague, who I promise will have a role here. I'm going to do most of the talking today, but Hugo will be here near the end to talk about our ensemble learning and boosted Reg Forest. So Hugo Watanuki is with me again. Hi, Hugo. Welcome back. And
Hello, everyone.
welcome to everybody out there. Thank you for joining us. Today, we're going to talk about GNN and boosted trees. And like in the old Smokey the Bandit movie, we've got a long way to go and a short time to get there. So we're going to get started right now. So, of course, we have, whoops, excuse me a minute. Of course, we have our travel quote for this session. Today's travel quote by the famous Mark Twain: "One must travel to learn." So today's journey, we're going to be traveling through actually the computer's idea of a human brain, neural networks. And then later on, we have one more trip through a forest. We're going to be going through the boosted forests and the ensemble learning, and that will conclude our journey for this 3-hour workshop. So in the first 2 hours, just to review, we talked about unsupervised learning in hour number 1. In hour number 2, we talked about supervised learning. In this hour, we're going to be looking at deep learning and ensemble learning. So we're going to be focusing on 2 additional bundles: our generalized neural network and actually our learning tree bundle, which has the boosted forests as part of the learning tree bundle. So that will be our presentation for today. So deep learning's been around for a long time, everybody. Since 1944, they first proposed it. They said, what if we can get a computer to act like a human brain? And so over the years, and many, many years, there's been articles, books, and then with the advent of the internet, all kinds of web pages and tutorials that have popped up about neural networks. So the neural networks also increased popularity with improved hardware. And this lesson today will focus on HPCC systems and ECL. So we're going to talk about how ECL deals with GNN, how HPCC systems works with neural networks through our GNN bundle. So once again, there's the idea of neural networks and a computer. Since we can just feed a computer a task, we started to say, well, why don't we feed a computer a task that is similar to how the brain works? So the neural networks get their name from being modeled loosely on the human brain. You have these neural circuits that have inputs and outputs and eventually get to a final output. Like, for example, you might have a pizza cooking somewhere and the smell of the pizza hits your nose, and all of a sudden your brain starts to say, that's a smell like a pizza. And then your stomach goes, I'm empty down here. And then your brain goes, I'm hungry. So that's, pretty much how the brain's working and pretty much what we do in neural networks. The inputs can change dramatically from the nose to the stomach to the brain. Eventually the pizza hits your mouth. So that's how neural networks essentially can be designed to work. So once again, you have a layer of information, and these layers can change, be radically transformed on their journey. And of course, then we apply weights and thresholds to influence the particular layer to give us a different type of output. And so we're trying to predict consistency, so that the next time we send the same kind of signal, the next time someone sends me a pizza, again, I'm going to do the same thing. I'm not going to go jump in the swimming pool. I'm going to want to eat that pizza. So that's kind of the same way with neural networks. We're training it to be consistent so that when new data comes in, we'll get consistent results. And of course, the thing that's made it really popular over the last few years has been the advent of these graphical processing units. So they more closely resemble the performance of a neural network. So by applying and allowing TensorFlow to work with graphical processing units instead of CPUs, we've achieved better performance, more accuracy. All right. And so this advent of GPUs and neural networks, we've been able to build bigger networks with our additional and more powerful hardware. So here's a graphical view of a neural network, very, very simple neural network. We've got a couple of inputs coming in from the left. We've got an output that's determined, and then in the middle, a hidden layer that AF stands for activation function. And the activation function, well, first of all, the W1s coming in are the weights that affect the different inputs, and more weight or less weight can affect an input affecting the output. And of course, then we can weight even the outputs of the hidden layer. And also B1 and B2, that's called bias. So we can actually bias a particular cell of our neural network so that that cell then will provide a stronger output or a more influential output to the eventual final output of our neural network. Now, these activation functions, first of all, we'll start with linear, which again, think of it as linear regression, like we talked about in hour 2, kind of a straight line type of processing. We have sigmoid, which is again related to more like logistic regression and classification. We have hyperbolic tangent, and then we also have this thing called ReLU, which is an acronym for rectified linear unit. And I want to stop here real quickly. It's the most commonly used activation function in deep learning. If it will turn to 0 if your inputs are negative, but for any positive input, it returns that value back. So it's very popular, especially with the type of image classification that we're going to be looking at in our examples. And we also have softmax, which is also used in multi-class classification problems. All right, so the beautiful thing, advantages of neural networks is that as we continue to feed inputs, their performance continues to increase. It's great for object recognition, excels with analog data, audio data, and so on. Works well with sparse data. I'm going to show you that in our examples. If one of the nodes or the neural nodes fails, the other nodes can kind of pick it up and still give you an acceptable result. And of course, HPCC systems, known for its parallel processing, makes it a good fit with neural networks. And again, once again, images, audios, nonlinear data. Disadvantages, it's black box nature. Sometimes we don't know why the neural network produced a certain output. It requires a lot of data to be accurate. Computationally, it's more intense then. It's going to take some time to produce those results. Sometimes it's hard to predict what type of neural network you want to use. So you have to kind of float between one and another and see how your results, if you're not happy with one result, then you can try another type of a neural network and see how that is working out. And then sometimes sampling estimates can produce an incomplete output. So we're going to be looking at our first two here, convolutional neural networks and then recurrent neural networks in our first two examples. Convolutional neural networks are popular with image classification because it's convolutional in the way that the inputs are cleaned up a little bit better. There's less pre-processing that needs to be done with convolutional neural networks before it gets to the actual layer. Recurrent neural networks are good when you need the output to influence the next input. And so now when we talk about things like word vectorization with sentences, our second example is going to be using that. And our intern that worked on that project decided to use with TensorFlow the recurrent neural networks, and you'll see how he set that up. There's other type of neural networks. One of my favorites was general adversarial networks. I don't know, I'm a fan of the show Billions on Showtime, and there's Chuck Rhodes against Bobby Axelrod, and they're always fighting each other. They're always adversarial, but sometimes they work together to go after a common enemy. And that's the way I look at the GANs. The GANs have two neural networks working at the same time, and then they kind of aggregate the results to produce new and synthetic instances of data that can pass for real data. So that's what we call a GNN. So once again, the traditional machine learning, we've talked about that in hour 1 and hour 2 when you have essentially observations and features. But anything that's dimensional is good for neural networks. Like we're going to be looking at our first example, which is images, which uses rows and columns and then 3 color values like red, green, and blue. How would you do that in another type of machine learning bundle? It just, you wouldn't know how to approach it. So anything that's dimensional is a great candidate for neural networks, anything more than 2 dimensions. So once again, now we're going to talk about how we get started with this. Of course, we've gone through this in the first 2 hours using the Git files that are tied to the ECL bundle in the Client Tools bin folder. In this hour workshop, we're going to be using the Machine Learning Core, the GNN bundle, and then the Learning Trees bundle. Once again, make sure that your command line in Windows is being run as an administrator. So these are the 3 installs that we're going to be working with in this workshop. And of course, you're going to have the PDF for this, so you can go back to this and reference this later on. I'm just going through this very quickly because we have a lot of stuff to talk about. So my next slide here is talking about the GNN bundle. And of course, the GNN bundle in HPCC requires Python and TensorFlow to be installed. Now, normally you're just going to contact your system administrator and say, please install TensorFlow for me. If you're working with your own cluster, these are the steps involved in installing TensorFlow. I've done this on my virtual machine cluster, and it worked very well. So these are the steps involved in working with your HPCC with TensorFlow. All right, and then after it's done, to test to make sure your TensorFlow was installed correctly, there is a built-in program called setuptest.ecl that you run. And you'll come back with each node of your cluster and whether your TensorFlow was a success or a failure. And it'll also tell you the version of TensorFlow that's installed on the cluster. All right, so now it's all about the tensors, GNN and tensors. What are tensors? Again, tensors, I would reference you to Richard Chapman's blog on the HPCC Systems website. He has a good introduction to tensors. And we had to develop a way, since ECL really doesn't support dimensions directly, we had to support a way of working with these dimensional tensors and then scaling them to work with ECL. So how did we do that? Well, first of all, we talk about tensors. Each dimension are known as shapes. So a 2-dimensional tensor has a shape of n comma n. A 4-dimensional tensor has a shape of n comma n comma n. What does that look like to all of you out there? Any of you that have used ECL, those are sets. So by working with sets, we can then emulate the dimensional shapes of tensors. I'm going to show you exactly how we do that in both of our examples. So then once we take this dimensional sets that will emulate these dimensional tensors, and then we convert them into record-oriented tensors called TensData, which is built into the tensor bundle. And I'm going to show you exactly where you get that record structure and then how you can't go wrong with it. For example, if you have a 50 by 50 color image, always the first element of the tensor is 0, followed by the number of rows, the number of columns, and then 3 representing the 3 colors of the image RGB. All right. And so we also have, in addition to the record-oriented tensor, the rectangular tensor, which is then converted directly to the TensorFlow interface. So there's 2 steps involved when you're creating an ECL tensor. Number 1, you create the data used to populate the tensor data record, and then finally you use any of the number of functions to convert it into the actual tensor that TensorFlow will then be using to work with the neural network model. All right, so here's some popular functions. The tensor data, as I mentioned to you, it references a module called R4, which is just an abbreviation for a real 4. And that's what they're just telling you, that's the tensor fields data type that's being used. And then we also have another function that kind of out of the box called to1hot, so that when you're working with tensors and you're going for a classification problem, like is this image a dog or is it not a dog, then you convert your Y tensors, your dependent variable tensors, to a distinct 2-state value, which will then improve the accuracy of the neural network model. And then we have some other functions here. The most popular one that I use all the time is make tensor. So that will take the tensor data and then make a tensor from it. Then we have from vectors and to vectors, and from scalars and to scalars, and from matrix and to matrix, which are used if you have vector data or scalar data. Or here's a cool thing. If you've used another bundle like linear regression or logistic regression, and then you discover that I want to see how this works in a neural network. Well, you could take the numeric field data set that you created in those other bundles and just apply it directly to tensors using the from or to matrix. And then you can then apply that to your Keras layer and then of course, your TensorFlow model. And so here we are. These are, now we're going to go outside the realm of VCL real quickly. As you can see here, triple single quotes designate that inside of these definitions is the actual string information that's going to be sent to the Keras layer, which we call LDEF, or our layer definition. And then we also have another definition, naming convention standard, called CompileDef, which actually tells us the settings to compile the Keras model, actually, talking directly with TensorFlow. All right, and then we have our GNNI functions, and in the order that they're shown here on this slide. That's the order that you need to consider them. We always start a GNN session with get session. We then define the model or the functional model. I'll explain the difference between that. Essentially, it's sequential versus non-sequential. Then we fit the model. Then we look for any losses. We evaluate the model. Then we can predict using test data. And then finally, we can evaluate the weights and then use them in additional models if we want to. If we're getting good results, we can get those weights and set those weights to another model that we're using to train. All right, and then finally in the GNN bundle, we've got some test programs for you to try out. So you've got a classic test program, which is the classic regression neural network. We've got human activity recognition, which actually has a data set for you to use. So you can play with GNN, spray the data to your cluster, and this person stood up, this person sat down, this person took one step forward, one step backwards. That's what we call human activity recognition, or the HAR tests. And then there's a classification test, a functional model test, which is different. It's a non-sequential Keras model test that you work with, and then you can work with multi-models. So these are all test programs that are ready to go, ready to run in your GNN bundle. I'd recommend that you run those first before trying your own data and your own neural networks. One more thing before I dive into the examples, we have a glossary here of terms. You'll see when you run your GNI test that you'll have in your information, in your syntax errors, you'll have a model ID, an epoch, LR for learning rate, batch size, and loss. And of course, the epoch is similar to an iteration. How many cycles does it go through the neural network? The learning rate is used to fine-tune how much to change the model on each epoch. The batch size is essentially how many records do you work with on each epoch, how many records per node, I should say. And of course, the loss is expressed in percentage on how far your predicted values deviate from your actual values. So we're going to look at some custom examples right now. I'm going to alt tab over to my ECL IDE. And for your edification and for this workshop, there are 2 tutorials that are provided for you. And we're going to have the link for you at the end of this workshop and where you can get these. There's a GNN example 1, a GNN example 2. And GNN example 1 is image classification. GNN example 2 is word vectorization. The GNN example 1 I'm going to go through quickly because that's also available in my online lesson for GNN. So you could go into it in more detail and look at it a little bit more, but essentially let's go through it real quickly. You can see here in this first ECL file that we're looking at, this is called file_image. And the way that we work with images in ECL is we first use a blob spray technique. So those of you that haven't sprayed using blobs would want to look at the programmer's guide on how to do that. Essentially, it's looking for the name of your file, and then it takes the binary data of that file and puts it into a data field. So that would be the first result of your blob spray. And then here is the actual file, the resulting file of the blob spray. And now I'm going to do something else with it. I'm going to enhance it a little bit by adding it a sequential record ID and then the dependent data or the Y type. In other words, in image classification, are these BMP files a dog or not a dog? And so very quickly here, a couple of projects I'm going through and then looking at the file names. And if it's a dog, I'm going to assign the Y type a 1. If it's not a dog, I'm going to assign it a 0. And you can see here, just for proof of concept, that I'm only working with 14 images. So yeah, you're not going to get very good results here. Here, but it's going to prove the concept and prove how you use GNN. And so then you can apply it to your 4,000 images like one of our interns did. And what good results she got from it by just basing it on this core model of image classification. Then she said, okay, well, let me give it 4,000 images. And then she got some amazing results. So here's the actual file that now has the image data stored. As you can see, it looks like a convolutional mess. And so that's the input data. Then we split it into training data, and then we split it into test data. And so real quickly, the first step in working with GNN, of course, is at the very top here. I'm going to go up to the top, and we'll start talking about building the tensors. So I want to thank Roger Dev for helping me through this, which again, we've talked about this in hour 1 and hour 2, that in order for you to be really good with machine learning, it's always good to have a data scientist at your help, so that you can then get some advice from them on how to construct things. So when we were talking about image classification, and we had that image in there, of course, my images were very small, 60 rows by 90 columns. And of course, your RGB was 3. So this was the total amount of tensor data that we had to build. And then using this algorithm right here, we then construct a kind of, well, not a kind of, the actual data that's going to be used by the tensors. So coming back over here to my results, you'll see that after I build that tensor, let's see, one more, there we go. So this is the output of that transform using normalize, where we've got a 1111, a 1112, 1113, and then the actual byte value of the image that's being stored in our value. So back over here, you can see there's the indexes that we're building. And again, it's just a set that we're putting into the indexes. And then the value, which is then translating the particular number in that image record and then putting it into the value field. So we do that, and then right after that, we build the tensors for that training data called tensor training. And then we do the same thing for the test. And then comes the magic. So then when we want to implement our GNN, we have our Keras layer right here, which is using, once again, the rectified linear units and the input shape and our layers. And this is a sequential processing, so we don't need to have a functional model here. So we have our compiler definition. We're using a popular optimizer called Atom, followed by categorical cross entropy for losses. And there's a ton of losses out there that you can look at and try. And my biggest advice to you about this is go out to the tensorflow.org tutorials, see what they're doing, and then you can actually then study the Keras layer and look at and say, well, let me try maybe this type of loss or this type of loss. But this is the recommended loss type that they recommended for the image classification. After that, we go to our get sessions. We define our model, we get our weights, we fit the model. And remember, the fit function has default values for batch size and number of epochs. I think the number of epochs is 1, and the batch size default is 512. But after a while, you'll start to play with these and you'll say, well, let me try 10 epochs. Let me try 20 epochs. Let me see how my losses are going to be changing. Let me modify my batch size based on the type of cluster I'm working with and so on. And then later on, you'll see you might want to play with the learning rate reduction and other factors in the fit. So we go through this, we get through it, we then evaluate it. And of course, I'm going to get terrible results with this because I only have a handful of records. So my accuracy was very bad. The loss was very high. And so I'm not even going to bother to show you that. I'm going to go to a real better example in GNN, which now we're going to talk about the word vectorization. So in this second example, GNN example number 2, we have actually 3 data sets coming in. And check this data coming in. A lot of zeros, a lot of numeric data, then we have weights, and then we have words. Look at that numeric data. So folks, we have in the sentence, we have 100 words per sentence. If a sentence is smaller than 100 words, we pad it with leading zeros. All right, weights. All right, well, what were we trying to do with this? Let me back up a minute. This project was called toxicity detection, where we were taking a sentence of words and then applying it to our vector and then determining whether that sentence was considered to be toxic or not. You can see that in weight number 7, if it's set to a 1 or a true, then the sentence itself is not considered toxic. If it's set like in number 7, if weight number 1 was set to 1, then that sentence was considered toxic. And of course, then we have the words, which is a 20,000 word dictionary. And get this, each word has 100 vectors representing that word. So this was the issue. We said, wow, we have 100 sentences with a possibility of 100 words, and each word has 100 vectors. How in the heck are we going to work with this in machine learning? And so the answer was, well, we went ahead and we created our tensors again. This time, though, a lot easier. We were going with a 100 by 100 model. So we have a word count of 100 per sentence and a vector count of 100 vectors per word. We have word count times vector count, once again, using a normalize of the total count. And we built our tensors just like we did in the image classification. The only difference in this one was, yeah, I did a little more of indexing because I had to store a way of getting into the vector file from the particular word. And thankfully, everything was automatically sorted. So if it was word number 20 in the vector file, that was record number 20 in the vector file, okay, or what we call the words file. So let's say in a sentence, I have word number, I have a word that's represented by a number 20. That number 20 would then be directly linked to the words file record number 20, and then all 100 values of that word would then be applied to that particular word in the sentence. So how about this for a sample? We use the first 10,000 sentences as our training data, and then we went through and we had our next 2,500 records as our test data that we were working with. All right, so we have our training data, we have our test data, and then the difference here was in the LDEF, where instead of using a sequential keras layer, we used a functional model. Our compiler definition, once again, using binary cross entropy and the Atom optimizer, and then an accuracy metrics model. We do the get session, but instead of defining the model, we actually referenced the elements from the functional model that was defined in the LDEF definition. And we said, okay, we want to use D1 as our start. We wanted to use so this D1 is your input. This mark right here in the inline data set was the output. And then from everything else after that, it was the same thing. Then we have our fit with our batch size and epochs and our loss. Again, 5,000 training records. Actually, I bumped it up to 10,000, so I had to change this named attribute. But I got excellent results with this again. Actually, I'm not embarrassed to show you the accuracy of this one because this was the real deal. And you can see that we only had a 26% loss with that number of sentences, and we had an accuracy of 91%. So that when we fed in new data it was 91% accurate that it would tell us if that was toxic or not. Now, just to show you, here was a smaller sample. And you notice a smaller sample of sentences, we had a little more loss, a little less accuracy. So the more that we fed to this model, the better it got. And the final result then, going back to our slides, is you can see for the image classification, after we fed it more images and we worked with and tweaked the Keras layer and the compiler definitions a little bit, we got an amazing loss thing, 9.2 times 10 to the negative 7th. So we had a great result with image recognition, facial recognition. That was one of our interns, Karina Wang, a shout out to you for the marvelous work that you did with that. And then also my other intern, Jeff Mao, who started with his word vectorization product, and I was happy to mentor. Here was working with sentences, and look how his loss started and went down to, once again, 29%. So that's GNN, everybody. So now we're going to go into our second type of bundle in our workshop, and we're going to be talking about ensemble methods using boosted reg forest. And the first thing I'm going to tell you is Roger Dev has an excellent blog on our HPCC Systems website. Here's the link. You'll have that in your PDF and you can follow it. And so, yes, in the learning tree bundles, we have simple decision trees that build into random forests. And we have gradient boosted trees that can actually build into boosted forests. So again, a forest is just a collection of decision trees. All right, so we have, standard decision trees that you ask it a question and it takes you to another point, another feature of your data and says, okay, is this true or not? Eventually you get to a final leaf that gives you a value. And the goal is to make sure that similar data will take the same path through the decision tree. So random forests, we build separate and diverse decision trees working together to eliminate noise, so we have a more consistent input and output. And then this helps us develop a set of tree models. For example, back in hour one, we talked about the rainforest and the tree aging. So if the height was greater than 50, then we look at the rainfall. If it's greater than 11, we go to another branch, and eventually we get to an age result so that a similar height and a similar rainfall will take that same path down the tree model. So in learning trees, it's very popular because it takes very little assumption about the data, can handle large numbers of records, large numbers of fields, nonlinear, discontinuous relations, works well with default parameters and without any fine tuning, and it's perfect for HPCC systems. All right, its prediction accuracy is also pretty good with the best state-of-the-art algorithms in the other machine learning bundles. Coming with the bundle is regression forest, classification forest, which we talk about in our machine learning tutorial in one of our online lessons. And the learning forest is kind of our base module that works with both of those random forests. And then we have boosted reg forest, which my colleague Hugo is going to be presenting here in just about a few seconds. Boosted forest is an ensemble method, a combination of gradient boosted trees and random forests, providing accuracy at least as good as GBTs and the ease of use of random forests. So it's, again, these ensemble methods take the best of each individual method, combine them into a composite and give you a better result. And they utilize something called boosting, which is a meta algorithm that is used to reduce bias and variance in your supervised learning and essentially converts your weak learners to your strong ones. So with that, I am going to stop my share right now and turn over to my colleague Hugo, who's going to show you a boosted regression forest.
Thank you so much, Bob. And while I'm sharing my screen, I just want to remind everyone, if you have a question, something that you saw, you want to ask something, feel free to post the question in the chat window. Either myself or Bob will reply to you promptly. So thank you so much, Bob, for that very precise and interesting introduction. And now I will take you through the second tutorial of today's session, which will cover gradient boosted forests. And before we start, I just want to make sure we are all in sync with the prerequisites for this tutorial. I'm sharing my screen here, and I'm just want to make sure everyone has downloaded the mod file from the hour 3 of this workshop, which will contain the code examples I'm showing and highlighting on my screen. And also make sure everyone has installed the Machine Learning Core bundle and the Learning Trees bundle, because the Machine Learning Core is a prerequisite for the Learning Trees bundle. And you can double check very quickly by expanding your bundles folder under your ECLID repository and make sure you see Learning Trees and ML Core bundle in that repository tree. Okay, so if everyone is good to go, I just want to briefly mention the purpose of this tutorial will actually be similar to what we saw in hour 2 when we tried to predict the prices of the properties using the linear regression bundle. But here, like Bob has mentioned, we will take advantage of one of the latest and greatest enhancements in supervised learning, which deals with not only leverages a decision tree approach, which kinds of makes us free from the linear or the expected linear relationship between independent and dependent variables. But we are also using a very powerful algorithm that will try to minimize the residuals between our predictions and the real values using a stage-wise approach, which is the gradient boosting itself. And it's a perfect combination for you to increase the power of your models when you have access to such a powerful parallel processing platform such as HPCC systems. So enough with talking, let's get started with our tutorial. And I'm sharing here on my screen the code examples that we are going to leverage here. You might notice a lot of similarity between the name of the files we're using. So by this stage, you should be already used to the name of the files we are using throughout these tutorials. As usual, we have a ECL file to define our data set. We have a prep file to prepare our data set for our machine learning algorithm. We have a convert ECL file to make sure we convert our record sets into the numeric field format required for our bundles. And of course, our train03 file, which will actually perform the training and the assessment of our model. And last but not least, we usually have a BWR file where we can follow along and make outputs of how our data is changing throughout this process. Okay, so I'm starting here with the file property ECL file, and you can see that this is pretty much the same record structure we have on our tree for the linear regression bundle. These are the fields describing the properties we have in our data set. And what I want to call your attention right now is make sure, just like we did in linear regression, we are still using a regression type of approach here. We need to make sure we are selecting only numeric fields. So on top of the basic fields that describe or characterize my properties, such as the assessed value, the year acquired, I need to pay attention to 3 specific fields: the property ID, which we will leverage as the identifier for our machine learning algorithm. Remember, most of our bundles require a identifier field for the data to be properly processed. So we will take advantage of the property ID field, and we won't need to create anything additional. And this time we are also taking the zip code information, perhaps to increase the quality of our model. But we need to be careful with zip, because even though it's a numeric field, the value of the zip code doesn't have any meaning for us in a quantitative perspective. So I will show you later on how to take care of that categorical characteristic of the zip code when we talk about the bundle and the training itself. And last but not least, we have the total value of the property, which is actually what we are going to predict here, our dependent variable. Okay. Now, once we have seen this file, basically, I would like to go over our BWR and make sure you uncomment, the first output, just to make sure you have your data set properly displayed. So basically, like I mentioned, it's the same data set that we use it on our 2 with all the fields describing the property, location, and its characteristics. Okay. Now, let's move into the prep01 file, where we will first format, clean, and make sure we have our train and test data samples ready. So just like we are using at this point in time, I'm adding here a randomic field just to make sure that our original data set doesn't have any kind of bias inbuilt into it. So I'm adding a randomic field, which I will later fill in with a random function, which will in turn provide a randomic number into that field. And I'm also taking some special care here to make sure I'm not carrying any empty or zero fields in some of the key fields for our property data set. And you can easily inspect that by using data patterns, as we saw, and have a better idea of what field types might have a quality problem up front. Now, in this prep step, I'm also making sure that my zip field is being converted to a unsigned tree type of value. And then I'm sorting this data set using the randomic field just to make sure I eliminate the bias completely. And last, I'm here taking a 5,000 record sample to train the model and a 2,000 or less than 2,000 record sample for testing the data, just for the purpose of this tutorial. Okay. Once you have your data ready, next step, make sure you convert it to the proper numeric field format for the algorithm. And that's what we are doing in the convert02 ECL file. So if we look into the convert02 ECL file, you will see that the first step that we take is to actually convert our train and test data into the numeric field. And this can be easily achieved using the toField function provided in Machine Learning Core Bundle. And that's why one of the reasons why I asked you in first place to make sure you have the Machine Learning Core Bundle installed before running this tutorial. And in case you are curious to see what the numeric field format looks like, I have left here 2 commented output statements that you can uncomment at your convenience and take a look at how those fields look like. So I have here separated a quick example just so you have a visual idea of how the numeric field looks like. So basically what I have here is the ID of a single property from my original data set. And in the number column, I now have all the 10 numeric fields that I am about to consider in my machine learning training algorithm. I'm still not splitting which variables are independent or dependent. I will do that next, but I'm just telling defining on my code here that I will be using 10 variables and the value of each variable is listed under the value column. So if I'm not mistaken, variable number 10 is actually the property price, and variable number 1 is the zip code. And here in between, I have the assessed value, number of bedrooms, and etc. Okay, this is just to make sure you understand what the numeric field format is. Now, one last step before I actually train the model, is to make sure I split my variables between independent and dependent variables. Since we are still working with, a type of supervised learning, I still need to take into consideration that I not only have my independent set of variables, but I also have the dependent values that I want to predict. And here I'm just filtering the numeric field format data set and making sure everything below 10 in the number column is actually my independent training variables, and the records in the line number 10 is actually my dependent training variable. And I'm just relabeling the number of the variable to be 1, just because I just have one dependent variable. Okay, so just formalizing my conversion before I'm ready to start the training of the model. Okay, now it's time for the magic. On the ECL file train03, this is actually where we are going to train our model. And once you reach this stage, everything is usually pretty nice and easy. So I start here by importing the learning trees and the machine learning core bundles. And I'm also start defining what my independent and dependent variables will be. And just to make it simpler for us, I'm going back to the math classes here and renaming my independent variables as xtrain and my dependent variable as ytrain. And same thing for test samples, okay? It will make easier for us to reference who is whom. No? Okay, so once I have specified my set of training data, I need to make sure I specify what my learner will be. And here on row 12, this is where I'm actually specifying that my learner will be a boosted regression forest bundle. And as a starting point, I recommend you to use to go with the default values. And here I was not able to go with the default values just because, remember, I have zip code field, which is not actually a numeric field, is a categorical field. So by specifying one between brackets, I'm telling the boosted regression forest function that my first field is actually categorical. So it will take into consideration for you. This is pretty nice functionality inbuilt into this algorithm. So once you have taken care of making sure you have selected your learner, most of our machine learning bundles, as you might have noticed so far, has a get model function where you pass your independent and dependent variables, and it will get you and extract you the model. And once you have the model, you can use a predict function to assess now the independent test set to make sure you can obtain predicted values. And based on the predicted values, you can use the accuracy function available under the machine learning core bundle to actually compare your predicted values with your independent test records. And from that comparison, we will extract the R-square coefficient, or the coefficient of determination, which will give us an idea of the predictive power of the model that has been trained. And I have that handy right here. So first of all, I have my predicted values. So for each property ID, we have the label of the dependent variable and its associated value. So these are actually the prices being predicted by our trained model for each of the property IDs. And lastly, we have the accuracy value for our trained model. In this case, 0.8876 approximately. And here, if you need to have an idea of how much error I have in average between the predicted prices and the real prices, you have here the root mean squared error for you to assess as well. So this is in a nutshell how you can actually work with the gradient regression forest bundle. But just like in the previous tutorials, there is always a question at the end. What do you need to do in case you're not satisfied with the quality of your model and you actually need to improve it? And just before we wrap up, I want to briefly mention a very nice functionality made available in HPCC systems. And actually there is a very nice blog from Roger Dev covering this functionality, which is the Myriad interface. So Myriad interface will allow you to actually leverage a single interface and train different models within the same data set by using all the power that we have in a parallel processing platform such as HPCC systems. And real quick, how can you take advantage of the Myriad interface? Basically, all you have to do is to make sure you add one additional field on your record structure. We call this work item ID, so you can label which records from your training data set belong to a specific category. So once you have added this additional field in your prep1 ECL file, and I have here on my repository all the ECL files with that underscore MI actually refer to the codes exercising the Myriad interface. And all I'm doing here is to basically populate the work item ID field with a label that will tell me if the property is located in the state of California, New York, or Florida. And each of these states will have its specific label. Once I do that, and I'm also make sure I inform my machine learning core 2 field function that I do have a work item ID field, the gradient boosted forest algorithm will take care of processing that specific field during the training of my model. So I don't need to make any changes to how I set up my model. But at the end, once you look at your end results, you will see that you now have 3 accuracy results, each one for one of the states you have specified on your Prep 01 step. So here you can see on a more granular perspective that actually the records belonging to Florida can give you a better predictive power for your model. So you can take into consideration, you can take these results into consideration and use the model for certain properties in certain states. So this is just one of the possibilities you have in case you want to optimize your model. Okay, so that's all I have for this tutorial, everyone. I hope you have enjoyed it. And before I turn over to Bob, I just want to make one final remark. We just saw one of the algorithms available in the Learning Trees bundle, but just like Bob mentioned, if you want to study more, get to know a little bit more on all the capabilities and different functions, I recommend you to look into your bundles folder under the Learning Trees, and you will see that you actually have additional code examples that you can try, including sample data sets that you can use to get you up and running with all the capabilities of the Learning Trees bundle. So don't forget, this was just the beginning, and I think the sky is the limit. So thank you again for your attention. And now I will hand over back to you, Bob, so you can wrap up.
All right, thanks, Hugo. Just go ahead and stop sharing if you would. There we go. And let me wrap up very quickly because we are running out of time. So thank you, Hugo, for that great demonstration. I'll leave you with a couple of travel quotes to wrap up our 3-hour workshop. Only one who wanders finds new paths. All right. But remember, not all those who wander are lost. All right. So remember, travel through these bundles, learn them, and we have a lot more to talk about in future workshops. Thank you for attending. And here's our emails. Here is the GitHub website to download the code examples. Thank you so much for joining us in the 3-hour workshop, and everybody enjoy the rest of your day. Thank you very much.